Assalamu alaikum, everyone. Good morning. Let's continue our discussion from where we stopped yesterday. So we were talking about the general entropy balance formulas, and we just said that the entropy that is entering a system through either heat or mass transfer minus the entropy that is leaving the system plus the entropy generation within the system should be equal to the change of entropy during any given process. So this is basically the change in entropy between any two states of a system. Same way, we can write this exact formula in the rate form by saying that the rate of entropy entering a system, either through heat or mass transfer or both, minus the rate at which entropy leaves the system should be equal plus the rate of entropy generation within the system because of irreversibilities will be equal to the rate of change of entropy within the system. All right. And we know that ds by dt is going to be equal to 0 for steady state, steady flow processes, simply because steady state, steady flow processes by definition do not involve any rate of change of properties. The properties such as the entropy, the energy, the mass of the control volume, all of this remains constant within a steady state, steady flow process. All right. And we know very well that the entropy generation is 0 for a reversible process and its positive number and non-zero for any irreversible process. All right. So this is how you would determine the entropy balance for any system. Okay. Now, if you want to determine or if you want to account for the entropy generation that is happening even outside the boundaries, we can certainly do it by writing an entropy balance on the extended system, right? On the system plus its immediate surroundings, such that we take the entropy generation in the immediate surroundings or the of the system also into account. Okay, so we do that in special cases when the question asks us to do it. For example, like we did in the previous examples, where we were asked to determine the total change in entropy or total entropy generation, right? So we sort of do that in such cases. Otherwise, we just are interested in applying entropy balance on a given system, be it closed or open, and then solving for it. All right, so with that, let's move forward and talk specifically again about a closed system. Now, for any closed system, the entropy change of that system during any process that it undergoes is going to be equal to the net entropy that is transferred through the system, which can only happen through heat transfer for a closed system because there's no mass transfer at all, and the entropy which is generated within system boundaries. So essentially what we are saying is, and we have said this before, so what we're repeating now is the change in entropy of any closed system can happen only because of, let's say, two reasons. One, entropy transferring into the system or out of the system because of heat transfer, plus the entropy generation. That's it. These are the only two situations where the entropy of a system will undergo change, right? Now, if you're dealing with an adiabatic system, adiabatic closed system, meaning a system where heat transfer is 0, then of course the entropy generation is exactly equal to the change in the entropy, right? Which means that the change in entropy for an adiabatic system has to be 0 or positive, right? So delta S for an adiabatic closed system, let's say, has to be equal to or greater than 0. Otherwise, the process is not even feasible. Okay. Now, if you want to take the entropy generation of the system and its immediate surroundings into account, we do that in this way by taking the entropy generation of the system. This part is nothing but the equation that we have written here, plus the entropy change of the surroundings. All right. So this is how you would deal for closed systems, closed system plus its immediate surroundings. Now, for delta surroundings, we have already looked at the formula before, but to remind you, it's again Q by T, Q surroundings by T surroundings, where T is the temperature in Kelvin of the surroundings, and Q is the amount of heat transferred to the surroundings, right? Now, let's talk about the entropy balance or entropy generation for a steady flow process. We're talking about an open system, right? A special open system where uh, the properties within the control volume do not change over time. All right. So in this case, we have, of course, heat transfer plus also mass transfer. So in this case, when we talk about the entropy balance, there are actually two ways for entropy to enter or exit a system. That is, the entropy can be transferred into the system through heat transfer, plus the entropy can also be transferred to the system through mass transfers, mass coming in and mass going out and taking along with itself some amount of entropy as it goes out and bringing along with it some amount of entropy as it comes in. This plus the entropy generation is again going to be equal to the change in entropy within the control volume. All right. So this is what is the general formula. Okay. Now we know that we can write a the rate form of this same formula in this way, where we can say that the rate of heat transfer divided by the temperature at which it's happening, plus the rate at which entropy comes in, along with the mass, minus the rate at which it exits, plus the rate of entropy generation should be equal to the rate of change of entropy within the control volume. Now, for steady state, steady flow systems, as we have discussed before, the rate of change of entropy within the control volume is zero. There is absolutely no change of entropy within the control volume itself, right? Which basically means that the the rate of entropy coming in through heat and mass transfers should be balanced with the entropy generation. Or for steady flow, we can say that the entropy generation should be equal to the entropy mass times the entropy that is exiting the system minus mass times the entropy that is coming into the system minus the entropy that's coming into the system through heat transfers. All right. So this is how we would calculate the entropy generation, right, for a steady state, steady flow system. Now, if you're dealing with a single stream, we don't need to have the summations. Okay, you can simply write entropy generation as m dot se minus si. This e standing for exit, I for inlet, minus summation of q by tk. All right, q being the heat coming into the system again. Now, if you're dealing with an adiabatic uh, single stream steady flow system, of course, the Q part goes out. And again, you can say that the entropy generation is simply equal to the rate mass times the change of entropy within the change of entropy in the control volume, the entropy that comes in minus the entropy that goes out. All right. And therefore, when we are looking for a single inlet, single exit steady state, steady flow system, like the one shown here in the schematic here, right? We can very well say that the entropy at the exit should be either greater than or equal to the entropy at the inlet, or we can say that the entropy of the substance either increases or remains constant. All right, and the entropy at the exit increases for all irreversible processes because, well, entropy generation we know is a positive quantity for all irreversible processes. Okay, and if we are dealing with a reversible process, then of course the entropy at the exit should be equal to the entropy at the inlet. Remember, this applies only when we are dealing with steady state, steady flow process, which is also adiabatic and it has single inlet, single exit streams, right? Basically, we're getting this from this particular equation, which says that the entropy generation is equal to mass flow rate times the change in entropy. And mass flow rate anyway cannot be negative. So the entropy generation we know is either greater than or equal to zero, which implies all these conclusions that we are sort of making it here. Okay, so this is how you would do it for a steady state, steady flow process. Let's go ahead and solve a problem. Before that, just to clarify here, the equation for steady state, steady flow starts from here. All right. Before that, when we talk about unsteady state, for example, right? So you can basically make use of the equation here at the top, right? So this equation would apply for unsteady state, uniform flow processes, right? So we started off with a very general formula, then we came up with the rate form, and then went ahead to come up with the form for steady flow. But the most general form is the one that applies for the unsteady state uniform flow process. And we will deal with problems for both of these cases, of course. I want to solve a problem for steady state, steady flow process in the recorded lecture because we have dealt with it very often. And Students in general are more comfortable with steady state steady flow process. We also have a solved example on unsteady state uniform flow. However, the unsteady state uniform flow is sometimes tricky for some students to understand. So I will not do it in a recorded lecture. We'll do it in the class on Sunday, inshallah. So now let's go ahead and try to solve this problem. All right, so what we're dealing with is a throttle valve, right? So we know that by definition, throttle valve is, we know by definition, a throttle valve is isenthalpic, right? So we have some information given here, and the idea is to basically go ahead and solve for the entropy that is generated within the system, right? Specifically the entropy generated per unit mass. So let's see how we go about it, right? So let's note down what is provided to us and we'll move on from there. So we are dealing with a water vapor that enters the throttle valve, right? Enters here at 0.7 bar and 280 degrees Celsius. So we know the pressure and temperature, which means that we can exactly determine the state for it. And it exits at 0.35 bar. Okay, so we know the exit pressure, but we don't know anything else. Now, for this case, we need to determine the entropy generated within per unit mass, of course, within the system, right? So this is a rather simple problem, as long as we know what we need to do. Okay, so let's note down what we have and what we need to determine. So we're dealing with an open system, one inlet, one outlet, and this the pure substance that we're dealing with is water. The inlet pressures and temperatures are given. The outlet pressure is given, and again, it's a steady state, steady flow device. So we know that the mass flow rate at the inlet should exactly be equal to the mass flow rate at the exit. Okay, so we are dealing with a steady state, steady flow substance. So it makes sense to basically write down the entropy balance for it. And we know that for steady state, steady flow systems, the rate of change of entropy within the control volume is going to be zero, right? So this term goes down to zero. So what we are left with is we are left with entropy generation being balanced by the entropy coming into the system and the entropy that's going out of the system, right? So here we have we can write as we can write this as m dot s1, which is the entropy coming into the system, minus s2, which is the entropy going out of the system, plus entropy generation is zero. Now, normally you would also have the heat transfer term in the general balance equation, but of course, the throttling valve is adiabatic, right? So throttling valve is always adiabatic. Okay, so we don't have to put in that term in the equation. So we are left with a very simplified expression, right? So entropy generation is simply equal to uh, mass times S2 minus S1. But here, since we are trying to determine entropy generated per unit mass, we are interested in entropy generation by m dot, which should simply be equal to S2 minus S1. So all we need to do now is to go ahead and determine S1 and S2. Now, S1 is very easy to determine simply because we know the pressures and temperatures already. So it's just a matter of going to the property tables. It's going to be superheated vapor. So just going to the property tables and getting the value. Now the question is, how do we determine the properties at state 2? We just have one property provided to us at state 2, and one property cannot fix the state. But we need to always remember that when we are dealing with a throttling valve, as mentioned here, in a throttling valve, the speciality is that it's the fluid undergoes an isenthalpic process, meaning H1 is equal to H2. So we have so we need to go and basically get H1 at the state 1 from the table, and that would be the second property that we use, right? So H1 comes out to be equal to 3035, and it is exactly equal to H2. And so now we have one property as enthalpy, second property as pressure at the exit, and so we have enough information to go ahead and determine the entropy at state 2 as well, because we can fix the state. And so when you do that and determine the entropy from the table, comes out to be 8.6295. So overall, we are just looking at entropy generation per unit mass. So it's going to be the difference between these two quantities, and it comes out to be 0.3133. So you can see it's a rather simple problem to solve. All it requires is to make use of the uh, entropy balance formula and then remove the terms which are not required and solve for it. Okay, so this is a very simple way to deal with steady state steady flow system. So now let's move on to another example. Okay, so here we're dealing with a mixing chamber, which again, from our understanding, is a steady state steady flow system. All right. Now here we have water at 200 kilopascal and 10 degrees Celsius, right? So 200 kilopascal, 10 degrees Celsius, which is entering entering the mixing chamber. It's entering at a rate of 135 kilogram per minute, which of course we got to convert to kilogram per second. And it is mixing steadily, right? This is the thing telling you it's a steady state process. It's mixing steadily with the steam, which is entering at, of course, the same pressure, but at a higher temperature of 200 degrees Celsius. So we have steam coming in at 200 kilopascal and 200 degrees Celsius. Okay, so we have cold water and steam mixing within the mixing chamber. Now the mixture, all right, the mixture of this water and steam, by water I mean liquid water and steam, it leaves the chamber at again the same pressure, of course, but a higher temperature, 55 degrees Celsius. Okay, and heat is lost to the surrounding air, so there is some heat transfer happening, and in fact, heat is being lost to the surrounding air. You have air in the surrounding at 20 degrees Celsius, and the rate at which heat is being lost is 180 kilojoule per minute, which of course we got to convert to kilojoule per second, so it becomes 180 by 60 kilojoule per second, or basically 3 kilowatt. Okay. Now we can neglect the changes in kinetic and potential energies like we always do. All we need to do is to determine the entropy generation during this process. So this is also another, let's say, not so difficult problem, but this one requires certainly much more thought than the first problem we solved. All right. So for now, let's note down the information that is available to us. All what we're trying to determine is the entropy generation, and we need to take into account the heat loss to the surroundings as well. Okay. So that's what we are trying to do. And the system that we're dealing with is an open system. It's a mixing chamber, so two inlet, one exit, and the pure substance that we're dealing with is water. So the inlet pressures and temperatures are given. The mass flow rate only for stream one is given. Okay, mass flow rate for stream two is not given to us. M dot two is question mark. And we are told that it undergoes the two streams mix steadily, which means it's a steady state steady flow process. And we have enough information about the exit mixture that comes out. It comes out at the same pressure uh, and a temperature of 55 degrees Celsius, which is somewhere in between the cold and hot streams, again as expected. Okay, so now let's go ahead and start by writing down the energy balance, sorry, the entropy balance equation. Okay, because we need, let's figure out what do we need here, right? So entropy coming in minus entropy out through heat and mass transfers plus the entropy generation should be equal to rate of change of entropy within the control volume. Again, it's a steady state steady flow system. We know this should be zero. So let's note down the things that are forming the rest of the terms. So let's talk about the entropy coming in. Now, the only way entropy coming in is through the mass transfers at state one and state two, or entry one and entry two. All right. So m dot one s1 plus m dot two s2. Now, the only way the entropy is going out is basically through two ways. One is going out through the exit here at state three, and also there's some amount of entropy is getting transferred along with heat transfer. So it's minus M3S3 minus Q dot out by TB, right? So this takes care of the entropy in minus the entropy out part. Plus, of course, the entropy generation is equal to zero, or we can rewrite this equation in the sense of by sending the all other terms to the right hand side and say entropy generation is equal to m dot 3 s3 minus m dot 1 s1 minus m dot 2 s2 plus q out by TB. Okay. Now TB is basically the temperature of the boundary at which this is happening, and we're going to take it as its surrounding, the temperature of the surrounding. Okay, so this is known. Q dot out is given to us. We have state two, right? We have the pressures and the temperature, so we should be able to get entropy at state two. And we again have enough information about state one, so we should be able to get entropy at state one. Same way with entropy at state 3. We have enough information here. The problem here is we have mass flow rate at state 1, but we do not have mass flow rate at state 2. And therefore, we don't even have the mass flow rate at state 3. Okay, so this is what we are lacking here. We do not have m dot 2. So we have absolutely no clue what is the rate at which how much is the flow rate that is exiting the system. So the question is then, how do we find m dot 2, right? We need m dot 2, m dot 3, so that we can substitute in this equation right here at the bottom and calculate entropy generation. So here again, the most obvious answer might seem that we apply a mass balance to it, but mass balance for such a system will simply say that mass coming in through all inlets should be equal to the mass going out through all exits, which says that m dot 1 plus m dot 2 should be equal to m dot 3. We don't know m dot 2, we do not know m dot 3, and you really cannot do much with the mass balance, right? So then we got to think a little bit more. And what we can see is that we have the temperatures and the pressures given for all the three states, both inlet states and the exit states. So the only possible way now for finding the mass flow rate at state 2 is actually by applying an energy balance, right? So that's exactly what we will do. So mass balance, as we have written here already, we do not have enough information to apply this. So we will apply the energy balance, right? Which is simply the same stuff, energy in minus energy out is equal to change in energy within the system, or the rate of change in energy within the control volume. We know that this part is 0 for steady state steady flow substance. So energy in should be equal to energy out, all right? So looking at the heat, looking at the mixing chamber, okay, so we have two inlets, one exit. We can easily note down the energy balance. Okay, so basically what is coming in is coming in from two inlets. So that's m dot h1 plus m dot h2. This should exactly be equal to what is going out. The energy is going out through one exit at state 3 and the Q out. This is the only thing that's available to us. Now, what we do is when we're trying to solve this, we don't want to have too many unknowns in this energy balance equation. So we're going to replace m dot 3 with m dot 1 plus m dot 2. Okay, so we make use of the mass balance equation here. And so when we rewrite this equation, it becomes q dot out is equal to m dot 1 h1 plus m dot 2 h2 minus m dot 1 plus m dot 2 times h3. Okay. Now the good thing is we have the pressures and temperatures for all the three states. So it's very straightforward to go and determine the entropies or the enthalpies or any of the property that you need for all these three states. Right now, the first thing that we would look for is state 1. Now, state 1, the pressure is 200 kilopascal, temperature is 10 degrees Celsius. Now, we know that this temperature corresponds to, this temperature and pressure corresponds to a compressed liquid state. So the way we're going to find the properties is just by approximating it. So enthalpy at state 1, we can say is approximately equal to enthalpy of the saturated liquid state at 10 degrees Celsius, which comes out to be 42 kilojoule per kilogram. Same way, same way we'll need to do something for state 3, where it's also compressed liquid state. So we're going to make use of H3 is approximately equal to HF at 55 degrees Celsius and get 230.23 kilojoule per kilogram. For state 2, it's very straightforward. State 2 is superheated vapor, so you get the properties directly from the table. No approximations required. So now we have all the enthalpies. We have these enthalpies in here. We have m dot 1 as well. Q dot out is also there. The only thing that we do not know is m dot 2. So there's just one unknown in one equation. We can easily determine it. And when you solve for it, m dot 2 comes out to be 9.692. So once you have m dot 2, we already have m dot 1 as well, right? Sorry, we already have m dot 3 as well, because m dot 3 is simply equal to m dot 1 plus m dot 2. So now we have enough information and we can basically go ahead and determine the entropies again, similar in a similar way to how we find the enthalpies. So for state 1 and state 3, these are compressed liquids. So you got to approximate it as the entropy of the saturated liquid state at the respective temperatures, 55 and 10 degrees Celsius. For state 2, it's straightforward. Go and pick it up from the table. Okay. So now when we look at the entropy generation formula, we have everything that we needed. We have the mass flow rate at state 3, which is simply m.1 plus m.2. m.1 we have, it was given in the question. m.2 we calculated by applying energy balance. S S3, S1, S2, these were all known because these were all easily found because we knew the exact pressures and temperatures, or we knew the states 1, 2, and 3. They were clearly defined. And again, the heat loss to the surroundings was also provided to us. The only thing got to be careful is to use these temperatures in Kelvin, right? So we got to convert 20 degrees Celsius to Kelvin, so it's going to be 293 Kelvin. So now we are ready to substitute all the numbers in here. M.3 is 144.69, S3 is 0.7679, minus 135, which is M.1, multiplied with the entropy at state 1, 0.151, minus 9.692, which is the which is the mass flow rate at state 2, multiplied by the entropy at state 2, plus, of course, the heat that came out of the system, 180 by 293, right? So now one thing that we are doing here is we did not divide the mass flow rates by 60. We kept the mass flow rates in terms of kilogram per minute. So the final unit that you get for the entropy generation is again in terms of gonna be per minute. Okay. So when you substitute that, it comes out to be a positive quantity as you would expect. Entropy generation should not be negative. You're mixing two fluids, and it comes out to be positive quantity as expected, and it comes out to be 18.33 kilojoule per minute Kelvin. So this is how you would solve it here. And the next problem is on unsteady state. So we will solve this problem in the class on Sunday, inshallah. If you have any questions, please feel free to get back to me.